In this video, we will discuss the first shifting theorem. This theorem is used when we are getting the Laplace transform of a function that is of the form e to the at times f of t. So previously, what we have are common functions that are of the form f of t. And we know how to take the Laplace transform of those based on a given formula derived from the definition of the Laplace transform. Now, if we consider the function inside the Laplace transform to be of the form e to the at times f of t, where a is a constant, then using the first shifting theorem, this theorem states that if Laplace transform of f of t is equal to capital F of s, then the Laplace transform of e to the at times f of t is equal to capital F of s minus a, which only means that the Laplace transform of this form of a function is just the same as the Laplace transform of f of t. The only difference is that you evaluate s at s minus a. Okay, so recall that, for instance, the Laplace transform of cosine kt is of the form s all over s squared plus k squared. So if I want now to take the Laplace transform of e to the at times f of t, your transform now will just be shifted. So using the first shifting theorem, you will just replace the s here by s minus a. So that will be s minus a over s minus a quantity squared plus k squared, if we are evaluating e to the at times cosine kt. Likewise, if we have sine kt, the Laplace transform is k all over s squared plus k squared. If you want to take the Laplace transform of e to the at times sine kt, you will just have to evaluate this at s minus a. So you'll have k all over s minus a squared plus k squared. For cos kt, we know the Laplace transform is s over s squared minus k squared. And so if it's multiplied by e to the at, then the Laplace transform of e to the at cos kt is just s minus a over s minus a quantity squared minus k squared. Laplace transform of sinh kt is of the form k over s squared minus k squared. So if it is multiplied by e to the at, then using the shifting theorem, you'll have k over s minus a squared minus k squared. And then Laplace transform of t to the n is n factorial over s raised to n plus 1. If we take the Laplace transform of the form e to the at times t to the n, you'll just have n factorial over s minus a raised to n plus 1. Laplace transform of t cosine kt, we know that that one is equivalent to s squared minus k squared all over s squared plus k squared quantity squared. So if it's multiplied by e to the at, then the Laplace transform of e to the at times t cosine kt is s minus a squared minus k squared all over s minus a squared plus k squared all raised to the second power. And Laplace transform of t sine kt from our previous lesson is it's 2 ks all over s squared plus k squared squared. And so if it's multiplied by e to the at, we just replace all the s by s minus a. So you'll have 2k s minus a all over s minus a squared plus k squared quantity squared. Now the idea is you don't have to memorize these new formulas. Okay? That's why we are deriving it from the original, from the basic Laplace transform of f of t, so that you will be able to see that we are just replacing again the s by s minus a every time that you are using the shifting theorem. So there are no additional formulas actually that are new to you in this given topic. Now, let's have some examples. Let's evaluate the following. Laplace transform of e to the negative 2t times cos 5t. If you may recall, we have a similar example last time, of evaluating this function, but we did not use shifting theorem. Instead, we replaced the cos 5t by its equivalent exponential form. However, since we already know the shifting theorem, then we can use that as an alternative solution to this given function. So, we know that, again, the Laplace transform of cos of kt is equal to s over s squared minus k squared. And so, again, it follows that the Laplace transform of e to the at cos kt is equal to s minus a all over s minus a squared minus k squared. So, from our given, our a is negative 2. So, ito siya. And our k is 5. So, that's what we need, in our shifted Laplace transform. Therefore, the Laplace transform of e to the negative 2t cos 5t, taking this form, is just equal to s minus minus 2 all over s minus minus 2 squared minus k is 5. Okay, so that's 5 squared. Or you have s plus 2 over s plus 2 squared minus 25. Now, we can expand the first term in the denominator since this is just a constant. The 2, when you expand this binomial, you'll be able to have a constant and you can combine it with the negative 25. So, I can have this further, simplify this further as s plus 2 over s squared plus 4s plus 4 minus 25. And so, ultimately, we have transformed to be s plus 2 over s squared plus 4s minus 21. For our next example, we can see that we have here e to the t times quantity to the t to the fourth plus 2. So what we can do first is to distribute the e to the t such that we can use the linearity property. So this one can be written as Laplace of e to the t times t to the fourth plus 2 Laplace transform of e to the t. Since 2 is just a constant, when you multiply e to the t, then you can bring it out of the Laplace transform. Now, for the second term, there's no problem with taking the Laplace transform of this, just a common function. Now, for the first term, we use the shifting theorem. So, recall that the Laplace transform of t to the n is again n factorial over s raised to n plus 1. And so, if you have Laplace of e to the at times t raised to n, this is just of the form n factorial over s minus a raised to n plus 1. And so, if I have Laplace transform of e to the t times t to the fourth, here your a is positive 1, and then your n is 4. So, taking the Laplace transform of the first term, we will have Laplace transform of e to the t times t to the fourth will be of the form 4 factorial over s minus 1 raised to 4 plus 1. Or 4 factorial is 4 times 3 times 2 times 1, that's 24, over s minus 1 raised to 5. And then we know that the Laplace transform of e raised to t is just 1 over s, In this case, our k is 1, so that's just minus 1. Therefore, combining these two, okay, the Laplace transform, okay, of e to the t times t to the fourth plus 2 Laplace transform of e to the t is equal to 24 over s minus 1 raised to 5 plus 2 times 1 over s minus 1 or 2 over s minus 1. Number 3. Laplace transform of e to the negative 3t cosine squared 2t. So since you have here a squared in your cosine 2t, we cannot just evaluate it as is and do shifting theorem right away. So we have to first use an identity that will make this function appear as a sum, okay, or a difference depending on what identity is applicable. So in our case, we can write this, okay, again, cosine squared theta is equal to 1 plus cosine 2 theta all over 2. Therefore, the cosine squared 2t can be written as 1 plus cosine 2 times 2t all over 2, or that is just 1 plus cosine 4t all over 2. So with this, we can rewrite our given as Laplace transform of e to the negative 3t multiplied by, you can write this as 1/2 quantity 1 plus 4 or quantity 1 plus cosine 4t. And then you can bring out the 1/2 outside, so that's 1/2 Laplace of e to the negative 3t times 1 plus cosine 4t. And then you can distribute. So you have 1/2 Laplace of e to the negative 3t plus 1/2 Laplace of e to the negative 3t times cosine of 4t. Again, the Laplace of e to the negative 3t is just a common function. So that's 1 over s minus k. For this one, the second term, Laplace of cosine 4t. The Laplace transform of e to the at cosine of kt will just be s minus a over s minus a squared plus k squared. And so, we have our Laplace transform now to be 1/2 times 1 over s minus negative 3. Laplace transform of e to the negative 3t. And then plus 1/2 times, so following this, you have s minus minus 3 all over s minus minus 3 squared plus your k is 4, so you have 4 squared. Simplifying further, you get 1/2 times 1 over s plus 3 plus 1/2 times s plus 3 all over s plus 3 squared plus 16. Or, that's 1 over 2 quantity s plus 3 plus s plus 3 all over 2 times s plus 3 squared plus 32. Fourth example, you have Laplace transform of t e to the negative pi t times sine 4t. So, again, we cannot just take the Laplace transform of this, no? Okay, because you still have a t multiplied to it. So instead of thinking of sine kt that is shifted, right, we think of t sine kt that is shifted. So you can rearrange such that this one goes with your f of t. Okay, so rearranging, you can rewrite this as Laplace of e to the negative pi t times t sine of 4t. And then we know that the Laplace transform of t sine kt is of the form 2ks over s squared plus k squared squared. So, Laplace transform of e to the at times t sine kt is equal to 2k s minus a over s minus a squared plus k squared quantity squared. So, plugging in the essential constants. So, from the given, you know that your a is negative pi. Your k is 4. So, from our formula, okay, we just plug in to evaluate. So, Laplace transform of e to the negative pi t times t sine 4t is just equal to 2 times 4 times s minus a. So, s minus a minus minus pi all over s minus minus pi squared plus k squared, so 4 squared, quantity squared. Or we have 8 times s plus pi all over s plus pi squared plus 16 quantity squared.